Before we can begin structural analysis, we need to know about the determinacy and stability of the structure. So that's the focus of this problem. We're going to classify three structures as determinate, indeterminate, or unstable. The key concepts we're going to use are converting real supports to idealized supports and classifying structures by comparing reactive forces with equations of equilibrium. Let's take a look at those structures that we're going to evaluate. Here are the three structures: a frame, a truss, and a complex beam. We're going to classify each of the structures as statically determinate, which means we'd be able to use just the equations of equilibrium to find all the internal forces and reactions. Indeterminate, which means we need some help from compatibility equations or assumptions, or unstable, which has its own set of issues. If it's indeterminate, we're going to specify the degree of indeterminacy. Let's start with the frame labeled as A. At A, we have a rocker, which acts as a roller. It only offers one reaction force. We have a pin at B, which restrains motion in two directions, so we get two force reactions. Now, although this is called fixed, that just means that the connection between the two members is fixed or rigid. It doesn't mean that motion is absolutely restrained. So we have, for unknown reactive forces, 3. We have 1 free body. So we'll compare the reactive forces to the number of equations of equilibrium, and we conclude that it's determinate. Now we need to check the reactions to see if it's unstable. Reactions are not parallel. That's good. And the reactions are not concurrent. They don't pass through the same point. Therefore, our conclusion of determinate stands. Now, what if we had separated the structure into two members, separated at that fixed connection? Then we would have this member and this member. We still have our 3 support reactions, but then we'd also have three unknown internal forces at the cut. So we'd have an R of the 3 external reactions or support reactions, the 3 unknown reactive forces at the cut for a total of 6. We have 2 free bodies. So when we compare our unknown reactive forces with my 2 times 3 free bodies, we still come to the same conclusion. I want to point out, it doesn't matter how many times we cut a solid structure, the conclusion will be the same. And by solid, I mean that there are 3 unknown internal forces at the cut. And here we have the truss. Let's start by looking at the support reactions. We have a roller, so it restrains motion only in the vertical direction at each end. So if we looked at a free body of the entire truss, it only has 2 reactions, and they are parallel reactions. Therefore, it is unstable. We could also count up the number of unknowns inside the truss and add them to the unknown support reactions, compare it to the equations of equilibrium, and we would still come to the same conclusion. Not enough support reactions. It's unstable. Now let's try the beam. If we ignore the pin inside the beam and consider only the unknown support reactions, we have a free body. Looks like this. We get an unknown along the length of the cable. It's fixed at E, so we get two force reactions and a moment reaction. There is a roller underneath this point B, so we get one vertical reaction, and A is also fixed, so we get two force reactions and a moment reaction. Our unknown reactive forces is 8. Our equations, or our free bodies, is 1. If I subtract my unknown reactive forces, or I take my unknown reactive forces and I subtract the number of equations of equilibrium, I get 5, which would imply that it's 5 degrees indeterminate. But we ignored that pin, and I think that's going to affect our answer. So let's break the structure into its two members. We'll have the piece from A to C and from C to E. We said we have at A two force reactions and a moment reaction. At B we had a vertical force reaction. Over here along the cable we have one force reaction, and at E we get two force reactions and a moment reaction, and at the cut, the pin that we released, we get two unknown internal forces. So now, if I look at my unknown reactive forces, I get the original 8 from the external supports, 2 from where I cut the pin to make it two separate members, and that's a total of 10. My number of free bodies is 2. When I take the 10 unknown reactive forces, subtract the total number of equations of equilibrium I have, I now get 4. It is 4 degrees indeterminate. That is our answer, not this. And here's the key. Whenever there is a pin in a structure, we must cut it there before we evaluate whether it's determinate, indeterminate, or unstable. So let's summarize what we learned. For the frame, we found it was a determinate structure because the number of unknown supports or reactive forces matched the number of equations of equilibrium. For the truss, we found it was unstable, and that's because of parallel reactions. Also because there are insufficient number of reactions, but even if we had added one more roller to provide vertical reaction, they still would have been parallel and it would be unstable. And in the beam, we found it to be indeterminate, and we calculated that it's 4 degrees indeterminate, and we saw that you have to cut the frame or the beam, either one. If there is a pin, it must be cut at the pin. Well done.